We're gonna get started. Thank you. We're gonna get started. Very happy to have Maya Kapoor presenting today. Maya is a first-year PhD student in our program, and she's has the impressive accomplishment of getting her first paper published. Or at least I think it's your first paper. Is that right? And congratulations. That's a great achievement, and she's going to share with us her research work. Maya, please take away.
Thank you. So, like Dr. Chu said, I'm a first-year student. I'm working right now in the CREST lab with Dr. Tom Moyer, and I'm also co-advised by Siddharth Krishnan. My research interests are in big data and machine learning applications for cybersecurity. And our recent project is called PROV-GEM, stands for Provenance Graph Embedding. And it's an automated provenance analysis framework that uses deep graph learning on system provenance graphs. So it analyzes those graphs and then does a classification of anomalous or non-anomalous, with the idea being, can we detect cyber attacks and then in a resilient system possibly adapt against those attacks? So before I jump into the actual model and all the experiments and results, I wanted to talk about some of the background of data provenance. So what is data provenance? It's the lineage of data. If you're a security analyst and you're looking at a log and you see some data point, we want to know, how did it get there? If we see a file, we want to know that Alice created it, then Bob modified it, this kind of thing. So the lineage of data shows the causal relationships of the data. There is a format called W3C PROV, which is kind of in recent literature been the standard. And it defines 3 different node types. So in the graph, nodes and edges. One of the types is entities, so that would be the data itself. Another type is the activities. So that's actions executed on the data, like modification, writing, etc. And then there's agents, so who exerted control over those processes. So data provenance we can model as a graph because a knowledge graph is a really great way of modeling complex relationships. So this is an illustration of this knowledge of a knowledge graph. You have people, you have historical figures, you have museums, you have locations. There's a lot of heterogeneity going on in this graph. So that kind of does represent the system when we think about it. You have processes, you have files, you have nodes or inodes, you have so many different things going on in a single system, and then you can scale that up to a distributed system. And just like as is depicted in this knowledge graph, you have multiple relations, you can have multi-graphs, you have directed edges. So typically provenance graphs are going to be directed acyclic graphs. So what would be the advantage of modeling provenance in this way? Well, the advantage is that it enables us to do the root cause analysis for resilient systems. So I've depicted this graph here, which we're all probably familiar with this at this point because of COVID. This is like a contact trace graph. So the idea is forward tracing and backward tracing. If you have a node, you notice some issue, you want to be able to figure out where did it get the contact from, where is it going with transmission. So this causal analysis can be applied in systems. And with provenance graphs, there's 2 properties here that we particularly want to capture when we're doing our graph learning. One is the spatial properties. So this is network science. You want to leverage the structural properties of the nodes, the in degrees, out degrees, betweenness, centrality, those kinds of things. Then you also want to look at the temporal properties. So if you can take your static graphs and model them in like a multivariate time series, you can look at cause and effect of what's happening in the system. So this is a provenance graph. It's a very small one. It's just a cut of the wget process. And in this graph, you can see that relationships between entities, agents, and activities can be described by these edge relations in directed, acyclic, attributed, multi-layer, heterogeneous graphs. So that's a lot of different characteristics of these graphs. First of all, directed acyclic, so you don't have any cycles in this graph. It's has the possibility of maybe using some tree structures here. You have attributed, so depending on how you capture this provenance, a lot of your files and processes may have certain characteristics. For example, in our project, we use Camflow, which is a Linux security module. And when Camflow records the data, it records things like Jiffy count and the security context. So these kind of features are very important for our model because we do a feature-based node embedding, which takes into account all of those features for the node, and we can do some anomaly detection that way as well. So there's attributes not only on the nodes, but also on the edges. Then there's also the concept of multi-layer. So as you can see in this depiction, from the task to the arg variable, there's two relations, was informed by and used. So you have that example of being multi-layer. But if you think about system provenance, this Camflow in particular works in the kernel space, but you also have provenance that occurs in the user space. You have browser level provenance. If you're looking at a distributed system, then you have network level provenance. If you're looking at different kinds of network architectures, then if you're looking at like SDN, then you have control plane and data plane layer provenance. So part of the research problem is trying to semantically associate all of those different layers together. So there's that, and then combined with the heterogeneity, as I mentioned, of all nodes, the attributes that the nodes have, they're going to be different feature lengths, not only depending on what the actual node is, but depending on your capture mechanism and what the data that you have, what you're working with. So the provenance graphs are a big data problem because even just a single host can create terabytes of data provenance over months and even years of lifetime. And then when you create a distributed system, of course, it multiplies. So what we want is an automated analysis that enables an efficient response to subtle attack. So a single analyst, obviously it's going to be near impossible to look at this graph manually and try to derive anything useful from it. So first is the issue of feasibility, then efficiency, and then lastly, subtle attack. So if you are looking at a log that you have data from in March, and then you're looking at something that happened in May, maybe there's small anomalies that a human may not be able to track, but some kind of recurrent neural network might be able to track those long-term dependencies. So in the big data problem, one has to determine the root causes of the attack, anomalous subgraphs, anomalous nodes, anomalous edges. So this has to do with granularity. If you're looking at the entire graph over all of time and you model it statically, then you're going to be looking at a really, really big graph. Or if you're going to cut it down into single event loops or cut it into a time series, well, you have to make sure that you're not cutting out certain dependencies because then you might miss an attack that happens over different applications. So you need to be able to zoom in and out on this graph. So that becomes kind of a data visualization problem as well. And then also in a resilient system, you want to determine a possible response or adaptation going forward. So the security problem for provenance graphs, there's two particular attack vectors that the deep graph learning methods we've been looking at really help with. One of them is an advanced persistent threat attack. So as I mentioned, these graphs can get really, really big. You're dealing with terabytes of data. This is especially true in an advanced persistent threat where you're looking at months of log data. So the low and slow attack pattern can also present an issue with concept drift because you can have a different context at the beginning of a month and at the end of a month in one system. And it doesn't necessarily mean that there's anomalies or attacks. The system might just be doing something different over time. So that's something that you have to manage if you are, for example, summarizing the graph and trying to compress the data. Another issue is with the granularity, making sure that you don't have dependency explosion, where you have everything linked to everything in the graph, because that's probably not really the case. Whereas if you have too much fine granularity and you cut everything based on event loops, then you might get incomplete dependency. This is especially true in things like SDN architectures or anything with a command and control server where you have, you might not associate things at the data plane together. Another issue is zero-day exploits. So when you're building a learning model and you're wanting to make sure that you also capture things which we don't know about yet, new attacks, you want to use unsupervised learning because that's going to let you train on benign data so that you can have a well-tuned embedding, which should capture patterns of normal behavior, which is something that we made sure to do in PROV-GEM. So what is the problem? Given a provenance graph G, where V is the set of nodes, E is the set of edges, A is the set of node attributes, and R is the set of all relation types, The goal of this work is to produce a rich, low-dimensional representation of G such that we can detect anomalous behavior in the system. So at the end of the day, it's a binary graph classification task. Does the graph represent something malicious or benign? So there is some related work in Provenance graph embeddings. The first one that we looked at was called Siegel. Siegel uses an autoencoder model, which has a long short-term memory network for the encoder and a multi-layer perceptron for the decoder. And it detects supply chain attacks on compromised trusted software installers. So from this work, we liked that it used unsupervised learning because it was able to train on the benign graphs. Therefore, in an APT or in a zero-day exploit kind of attack, it would be able to pick up on something anomalous. But the Siegel architecture, or the Siegel framework, was looking only at a limited problem size. They were only looking at software installers, and we wanted to find something that would be more generalizable to all provenance graphs. And Siegel also suffered from a high false positive rate, so there was the risk of alert fatigue with their method. Another instance that we were able to actually compare against in our experiments was StreamSpot. So StreamSpot and Unicorn in both of our experiments, and we were able to compare against both of those, but Siegel did not share their data, so we weren't able to compare against them. But StreamSpot uses similarity hash-based graph sketches of a streaming graph, and then clusters it using k-means centroid-based clustering. So the similarity hash is an interesting approach because it does provide that constant fixed space for memory, which definitely helps with the dependency explosion problem and helps with just the big data size. But the way that StreamSpot did their similarity hash is a little bit misleading compared to like the Unicorn, which is serialized. They did a shingle-based embedding model where they cut up the features, and the way that they hashed it ended up creating some incomplete dependencies. The Unicorn model instead used a serialized embedding model, but this ended up creating some over-summarization in their hash-based graph sketches. In addition, their use of the Weisfeiler-Lehman graph kernel algorithm does have some processing limits. So our model actually is able to be more computationally efficient while still having similar results in classification. So what are the contributions of PROV-GEM? First off, we use multi-embeddings to capture the complex topology of the heterogeneous provenance graphs. So multi-embeddings, we have embeddings based on the node neighborhood, and based on the structural properties of the node in the entire context of the graph. We also use smaller convolutional neighborhoods to reduce the computational complexity and improve training stability. We use rich embeddings, which are learned through multi-relational semantic contexts. And lastly, PROV-GEM is generalizable and scalable for any provenance data. So for our data sets, as I mentioned, we were able to use the data from StreamSpot and Unicorn and their results and compare against that. So the StreamSpot data set, the benign data was browsing data from YouTube, Gmail, playing video games, downloading software, and viewing CNN. And as you can see, so for each case, we had like a 5-to-1 ratio of benign to attack graphs. And we trained on the benign graphs and then tested on the attack graphs. And as you can see, the StreamSpot graphs were a little bit smaller than the Unicorn graphs, but overall, they're still very big graphs. The Unicorn set, the benign data was wget installations, just installing that software. And for the StreamSpot data set, there was a drive-by download attack. So this is where the root access to the host was gained via an Adobe Flash vulnerability being exploited. And the Unicorn attacks, they were both supply chain attacks. One was a Trojan horse that exploited a vulnerability in wget version 1.17, and there was a shell shock attack as well, where Bash was vulnerable to remote arbitrary code execution. So for the Unicorn data, that was captured using Camflow, which is a Linux security module which captures the fine-grained whole system provenance. So it uses net filter hooks and security hooks inside the kernel space. So when those system calls are made, then it uses a daemon to convey that to user space. And it writes that either to a graph database or a log output. And so from those CAMFlow logs, we designed a graph generation framework, which would take those and then put them into a provenance graph. And from that, we also designed the embedding model. So for the different features, first of all, inside our graph framework, we created a locality sensitive hash value, which we were able to normalize the heterogeneity of the nodes doing this. So our thought was, with the CAMFlow nodes, as I mentioned, they have different types. So you have process, you have file, you have inode, argv, all kinds of things. And they all have a set of features that CAMFlow records. So there are certain things like Jiffy count. If something occurs within the same time, then it's going to be likely that those things are related. If something has a similar security context as described by CAMFlow, then those things are probably going to be related. So we were using this concept of being locality sensitive hashing to semantically associate those for each node. So we would use the hash, assign those nodes a bucket based on that hash, and use that as part of our embedding model. Then we also created relation-specific latent representation of the nodes based on the neighborhood context. So that was a one-hop neighborhood. And then lastly, we also use like the network X graph to look at the degree of nodes for structural property analysis. So to go through the actual neural network model, the PROV-GEM model, the first step is to encode the complex graph G into a low-dimensional spatial representation using an inductive transformation function. Then for the learning part, first we generate the latent representations, as I mentioned, based on the edge type for each node based on its one-hop neighborhood. So these are relation-specific, and we use a multi-layer perceptron with 2 hidden layers and an ELU activation function. For the next step, we apply semantic attention to the concatenated latent representation sequence. So here we take those latent representations and we concatenate them in sequence, then apply the semantic attention, which lets us derive attention weights, and then we normalize those using softmax. And finally, we use linear combination on the attention weights and the latent representations, and that lets us generate the final optimal embedding. And then we use a readout function to create the feature representations. Then for the classification, we use a 2-layer MLP with ReLU activation function and a final sigmoid activation to predict the probability of the attack class. And we use binary cross entropy loss to jointly train the encoder and the classifier. So the advantage here is while StreamSpot and Unicorn focus on graph summarization, so they use their hashes to try to control the size of the graph. This doesn't work for them because it leads to incomplete dependencies. We use parallelization and the scalability nature of the graph convolutional neural network to make PROV-GEM a more wholly contextual solution in provenance analysis. So what were our results when compared? Well, PROV-GEM performed comparably well or better in the classification task. For our advantages, first of all, we required only one-hop neighborhoods when applying graph convolutional filters versus Unicorn's 3-hop model. So, and that's based on the Wallace-Feather-Lehman graph kernel. So we're a little more computationally efficient there. That's great. We also are able to emphasize the semantic context of nodes. So versus just increasing our breadth and complexity of analysis, we can reduce the complexity and get more of a semantic picture. Our solution is also trivially parallelizable through node batching. So that's just the advantageous nature of the GCN. So as I mentioned, I'm a first-year student, and this is our kind of pioneer work into provenance and graph learning. So there are still a lot of questions that we want to answer. So I'm just going to take some time to go through some of those. First of all, multi-layer provenance. So system level provenance captures the kernel access, security context, file reads and writes, like I was saying with CAMFlow. There are several other systems to capture many other kinds of provenance. There's application level provenance. There is like provenance that captures execution partitions, that kind of thing. There are forms which capture network provenance. There's specific new research being done in SDN provenance. There's browser provenance, database provenance, so much. So how do we semantically tie what's happening at the kernel level with what's happening at the application level? to create an accurate and complete picture, particularly when we go back to the analyst and try to show them what's going on. So how do we also then, if we have all of this stuff put together, partition it efficiently to mitigate dependency explosion? In a distributed system, this idea of provenance capture can become more difficult because the semantics can vary depending on network architecture and security rules. And then for user systems and privacy, we're capturing a lot of data. How do we ensure that we're, one, meeting classification requirements if we're working on a government system, and then two, maintaining user privacy as we go in and out of layers. From just an experimental standpoint, one thing we ran into with PROV-GEM is that there's not really a good reproducing framework for provenance graph generation. So that's a future work for us that we're going to be looking at, is trying to create automated provenance generation frameworks that are generalizable and not just for like one particular kind of problem, because we want to look at having dynamic data and not just having static repositories of data. But in line with static repositories of data, those don't really exist for provenance either. The ones that we use, StreamSpot, was pre-processed. Unicorn only deals with the wget instance. And the other data that's been used in other works is not really meant for this. DARPA, transparent computing dataset, has been used, but that's not really what it's for. There hasn't really been any work in generating those datasets. So another question that we have is for return-oriented programming and gadget-based attacks, or anything that would be non-anomalous code. What happens when the execution is anomalous, but the nodes and edges are not, or vice versa? If you have a piece of malware that is installed as normal, so it looks normal, can that be detected in a normal subgraph? And in addition, Siegel was the only one to cover adversarial attacks. So there's not really been a lot of work in, if the attacker knows what's going on, or the attacker has some idea of the graph, can they change it and try to adapt? And lastly, in graph learning, so we are looking at a hash-based embedding model as well. The locality-sensitive hashing does provide efficient computation compared to like vector-based math, and it can provide a fixed storage space. And there's been some work done with cosine similarity, as I mentioned with StreamSpot, but some of the other similarity measures like Jacquard similarity and spectral-based hashing haven't really been explored. And also, as I mentioned with StreamSpot, their shingling kind of led to incomplete dependency. And with Unicorn, there was over-summarization. So both of those, it's kind of a balance of trying to make sure that doesn't happen with hashing. And we're also looking, if we're going to use a hash-based model, what about a sublinear classification strategy? So if using that hashing, can we optimize the data structure used for clustering instead of k-means or some kind of centroid-based? Could we use forests? Could we use something else? And lastly, for resilient adaptation, of course, for a resilient system, once we detect an anomaly, can we adapt to that? Can we assign intent based on that anomaly? So I've provided my email here, and I also listed the 2 other student authors for this paper. Definitely feel free to reach out to me if you're interested in any more of this, and I really appreciate your time. And if you have any questions, I'd love to hear it.
I have a quick question, Maya. Thanks very much for the presentation. I didn't get a really good feel of so it looks like you're doing unsupervised learning, is that right?
Mm-hmm.
And then you're trying to identify attacks, like a drive-by downloads. But do you have a specific example of how the intuition behind it, how that is carried out? I mean, what the difference in the graphs might be like, and then what lead to this particular approach? It's just like I'm sure the technical details are strong and are absolutely, I mean, I have no reason to doubt it, but I'm just trying to understand what is the intuition behind it.
Yeah, so I didn't include the picture in this presentation, but if the Siegel paper actually has an example of this, where if you have a software installation and the way that they did their data set was they bundled a piece of malware with a trusted source, trusted installation. And so when they actually showed the picture of the graph, there appears an anomalous subgraph that will be structurally different, of course, than your regular benign installation. So if I had that picture, I'd show it. But yeah, there is, in those instances, there is some different characteristic of the graph. But as I mentioned, that's one of the research areas that I'm kind of curious about, is if we have something that's more gadget based, where we're not bundling, or our malware is a little more hidden, or it's not quite as explicit. How does that affect the anomaly detection? Hasn't really been covered yet. So definitely a question to look at.
Okay, thank you.
Mm-hmm.
Anyone else? All right, well, thank you very much. And if you have any questions, anyone has any questions, please contact Maya. Thank you.
Thank you.